Hello. In a recent lesson, we discussed quartiles using box plots, and we learned that box plot organizes data by quartiles into 25% sections. But in addition to using quartiles, one could also divide the data into deciles or percentiles, or technically, any equal parts that they'd like. The most common ones are probably percentiles and quartiles. Percentiles are used heavily in the education and health medicine fields. Measurements above the 95th percentile are said to be unusually high, and measurements below the 5th percentile are said to be unusually low. That really comes to us from the empirical rule that we learned about when talking about the normal distribution. We say if you're more than 2 standard deviations away, that's on the above end would be higher than 95th percent, or on the low end below the 5th percentile, then we call that unusual in mathematics. But like I said, you could technically do not just quartiles or percentiles, you could do deciles, split your data set into 10 equal parts. The most common ones are probably quartiles and percentiles though. So we're going to start by looking at an application of using percentiles. So the ogive below, or cumulative frequency distribution, shows how one could easily determine the percentile and the score that it relates to on the SAT. If you scored in the 62nd percentile, what score did you actually get? Well, that's denoted in the graph shown by the dashed line. So 62nd percentile here, I can see relates to a score of each of these individual tick marks are going up by hundreds. So that would relate to a score of 1600, which means this. It means if you score 1600 on the SAT, in that format of the SAT, you are scoring higher than 62% of other test takers. This was when the SAT was out of 2400. I can also use it to go the other way around, not just look at what percentile relates to what score, but if you got a certain score, what percent with that percentile would you be scoring higher than? So if you got a 1500, approximately what percentile were you in? 1500 is shown right here. And if I go over, it looks to be approximately 50 percentile. So you'd be scoring approximately 50%. You'd be scoring higher than 50% of other test takers. So, approximately 50th percentile if you scored a 1500. So that's what the benefits of using a percentile. It gives you an idea of what percent you're scoring higher and lower than. If you're at the 50th percentile, you're scoring higher than 50%, but you're also scoring lower than 50%. That's the median. In order to calculate a percentile, if you have the raw data set, this is what we do. To find the percentile that corresponds to a specific data entry, call it X, use the following formula. We take the number of data values that were less than that score and we divide it by the total. And then we multiply by 100 because we want a percentile out of 100. And then we usually round to the nearest whole number. We don't do like 83.2nd percentile, so we would say 83rd percentile. So below are the tuition costs in thousands of dollars for 25 liberal arts colleges. Find the percentile that corresponds to $30,000. So the first thing I need to do is find $30,000, and it's shown right here. And then I need to calculate, count the number of data entries less than X. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 less than 30,000 divided by, they told me that there were 25 in total. So 9 divided by 25, and I multiply by 100 to get it to be a percentile. When I do that, I'm going to find it's the 36th percentile. And that is how you calculate a percentile given the raw data set. I'm going to give you a chance to try. So taking the same data set we had a second ago, I want you to now tell me what would be the percentile that corresponds to $44,000. Also, to kind of extend your knowledge a little bit, I'm going to ask you an extension question. Can there be a 0th percentile? If you go back to the definition, number of data entries less than that value divided by the total times by 100. Can there be a 0th percentile? If so, what is it? If not, why? Can there be a 100th percentile? If so, what is it? If not, why? So can you use the basic formula to find the percentile corresponding to 44,000 and then try those two questions. Pause the video now before I go through them. Okay, the first one was just simply finding the percentile for 44,000. Well, 44 is right here. It's on the higher end. And there's two ways you can do this. I want to find the number that are below 44, and that's a lot of counting. So instead, I'm going to count, okay, I've got 44, and then 45, 45, and 46. There are 4 values right here, and I know that there are 25 values in total, so that means there must be 21 that are below 44. So 21 divided by 25 times 100 tells me that $44,000, that's in the 86th percentile of college tuition costs for the liberal arts colleges that were in this study. Next part asks, can there be a 0th percentile? And there can be a 0th percentile. The 0th percentile in this case would be the lowest one, 19. The reason why is because there are 0 values in the data set that are below 19. Can there be a 100th percentile though? There cannot be a 100th percentile based on this definition, because even if I pick the highest value, 46, there are 24 values below 46, because 46 is the 25th. So 24 out of 25, even 46 in this case, would be the 96th percentile. So there can't be a 100th percentile because there's no value that is in the data set that also has all of the values below it, because it is inherently in the data set. So that's just an interesting question based on the definition, and definitions are important in math. That's as far as really we go with percentiles. The last part of today is talking about the second topic, which is something called Z-scores. And Z-scores are incredibly important in statistics. They're the basis of a lot of items that we're going to use in inferential statistics. And so we're going to begin with a kind of a simple idea, hopefully something you have some natural tuition, and then build some mathematical definitions from that. So start with the following question. What is more unique, a 6-foot-tall man or a 6-foot-tall woman? And explain. Well, I would probably guess that just based on people's intuition, we would say probably a 6-foot-tall woman. And maybe some explanations you might give would be, well, the average woman maybe is around 5'6", maybe. I really don't know. But the average man I know is taller than that, and so it's probably closer to 6 foot. So a 6-foot-tall woman is going to be further from her average, is probably what most people will say. And that's a mathematical definition that we use as well. In order to find what we call a Z-score, we want to find how far away a value is from its average. And by how far away, we mean how many standard deviations away you are from your average. So mathematically, you compare two measurements to determine which one is more unique by comparing their Z-scores. What we're simply doing is finding difference. But when we say difference, we're going to be talking about number of standard deviations from the average. Is probably higher for women in this case. And the actual rule says the following. So what we do in order to calculate what we call a standard or a Z-score, it represents the number of standard deviations a value lies from the mean. What we do is we take the measurement, we subtract the mean. We find how far away it is from the mean. So that's this portion right here. This is the how far away it is from the mean. And if we want to know how many standard deviations that is, then when we divide it by what one standard deviation is. So just a couple facts about Z-scores before we go calculating them. Well, a Z-score can be negative, positive, or 0. If it is negative, the measurement is below the mean. If the Z-score is positive, then that measurement is above the mean. If the Z-score is 0, it means that you are exactly on the mean. You are 0 standard deviations away from the mean because you were exactly on it. So Z-score is nothing more than number of standard deviations away from the mean. Now I have the actual data values. We can use it to determine which one is actually more unusual, a 6-foot-tall man or a 6-foot-tall woman. So let's do the first. So the men's one is 69.9 inches. So standard deviation Z is equal to, if I go back to the definition, I'm going to take the actual measurement minus the mean. So the actual measurement, a 6-foot-tall man, 6 feet. If I want to get it into inches, I simply do that in 1 foot. there are 12 inches. Just doing a little dimensional analysis. If you've taken a chemistry class, you've seen this before. So 6 times 12 is going to leave me at 72, I believe. Yep, 72 inches. So 72 minus 69.9, that is going to leave me at 2.1 inches. So that means a 6-foot tall man would be 2.5, or sorry, not 2.5, 2.1 inches above average. Well, one standard deviation is 3 inches, so I need to divide this by 3. So if you notice, a 6-foot tall man is not even one standard deviation above the mean. It's 2.1 divided by 3, because 3, I need to be 3 above the mean in order to be one standard deviation. I'm only 0.7 standard deviations above. Because this is positive, this is going to be above the average. So this is for z-score for men. Z-score for women would be, again, if we had a 6-foot tall woman, 72 minus average is 64.3. When I simply do that, 72 minus 64.3 is going to be 7.7 inches. So a 6-foot tall woman is 7.7 inches above average. One standard deviation for women is 2.6 inches. So I'm going to divide this by 2.6 inches to see how many standard deviations that is. And if I take 7.7 divided by 2.6, I see I'm going to get 2.96 standard deviations, or approximately 3. So I can look right here and see that a 6-foot tall woman is 3 standard deviations nearly above the average, whereas a 6-foot tall man is not even 1 standard deviation above average. So we would say, which would be more unusual? A 6-foot tall woman is more unusual because it's more standard deviations away. It would be a higher z-score. That's what we're looking at. That's what we mean by unusual. A larger z-score, more standard deviations away. We can use a z-score and then also relate it to the empirical rule. So a z-score is how many standard deviations away. It's the x-axis of my bell curve normal distribution. Recall that if you are 1 standard deviation above or below, that's 68% of the data. If you are 2 standard deviations above or below, that captures 95% of the data. And we use this to determine things that are unusual. So if you are within the 95% of the population, that's going to be within 2 standard deviations, we say that that is what we call usual. There's nothing unusual about that. That's the majority of people, far more than the majority, 95%. However, if you are more than 2 standard deviations away, we're going to start to say that's unusual because you fall within 5% of all people. So here's the following rule. When a distribution is approximately bell-shaped, you know from the empirical rule that 95% of the data are within 2 standard deviations in the mean. So when this distribution's values are transformed to z-scores, what we did a second ago, 95% of the z-scores should be between -2 and +2, because that's 2 standard deviations below or 2 standard deviations above. A z-score outside of this range will occur only about 5% of the time and would be considered to be unusual. So according to the empirical rule, a z-score less than -3 or greater than 3 would be very unusual, with a score only about 0.3% of the time. So if we go even back to the one that we just did with heights, a 6-foot tall woman, that right there is almost right on the 3 standard deviations away. So a 6-foot tall woman, by definition in statistics, is almost very unusual. It's in the range of only 5% of women would be on that, and actually 2.5%, because that would be on the high end, half of 5%. So we would say that would be an unusual, almost very unusual case based on the distribution of all people in the population. And then last part we're going to do is tie these together with some calculations. So this is where z-scores and statistics become very useful in determining what % of items are going to be lasting a certain amount of time, or people have a certain weight or height or all these things, or SAT score. So a light bulb company produces light bulbs with an average lifetime of 1,000 hours and a standard deviation of 75 hours. Use the empirical rule to answer the following questions. What percent of light bulbs last between 925 and 1,075 hours? So the first thing I need to know are what the z-scores of those values are. So the z-score for the 925, so 925 minus 1,000, that is going to be negative 75. It's negative because it's below. So that's how many hours? That's 75 hours less than average. So that light bulb fell short of the expectation. A standard deviation for light bulb lifetime is 75 hours. So that would actually be one standard deviation below. 1,075 hours would be 1,075 minus 1,000 divided by 75. So that's 75 hours above the expectation based on the mean. And the standard deviation for light bulb life expectancy is 75 hours. So that would be one standard deviation above. So now we're back to the empirical rule. What percent of data for a normal distribution, and that was expected in this situation, it would be implied. I would give that to you, and I'm giving it to you right now by saying that it is a normal distribution. What percent of the data are between -1 and +1 z-scores? Well, that's within one standard deviation. If I go to the normal distribution, I see that's 68% of the data. So 68% of light bulbs are going to fall between that many hours. You can imagine if you were like well, maybe you produce tires, you work for Michelin or something like that, you might want to know how long your tires are going to last in order to determine warranties or things like that. So you can see where we're going to be going with these applications. What percent of light bulbs last more than 1,150 hours? So the z-score for that would be, well, I need to do 1,150 minus 1,000 is the average. That's 150 hours above expected, divided by 75. So that is a z-score of 2. So what percent of the data for a normal distribution are more than 2 standard deviations away from the mean? Let's break this down. I know this is the median and the mean. This right here captures 50% of the data. Between 0 and 2, if I go back, this right here is going to capture, so 0 to 50% are below the mean. 95% fall in between -2 and +2, which means 5% fall with outside that. So for this one, I know there's 2.5% that is going to be below, and 2.5% that is going to be above. Because that's 2.5% that's going to be above it, I already know this right here is 2.5%, because this right here is going to be my 47.5% that comes from the combination of half of 68 and half of the remaining that is subtracted from 95 and 68. So I get 2.5% is going to be left in that far right. So 2.5% of light bulbs are going to last more than 1,150 hours. Going to give you a chance to try this concept by supplying you with a distribution and asking you to match the z-score with the score. So either option A, B, or C. Pause the video now and then come back once you've had a chance to try. Okay, so this is just a basic understanding. Do you understand that z-scores, when they're positive, have to be above the mean, when they're negative, they're below the mean, and when they're 0, they're on the mean? First one would be, well, the middle. Z equals 0 would be on the mean, and I can see that's going to be right there at 63, so that's B. If you have a z-score that you're positive, it means you're above the mean. That has to be C, and this is the negative when you're below the mean, so that has to be A. So B, C, and A. And that concludes our discussion with percentiles and z-scores. Thank you very much, and have a good day.